Today we are going to look at Linux x86 assembly language programming covering 64-bit operating system. Here are the topics we're going to look today. We'll start with an overview of CPU architecture. We'll look at memory and registers, addressing modes available in 64-bit operating system, instruction set overview, which talks about what kind of instructions are available for our assembly programming. Well, then we'll dig deeper into system calls and how it interfaces with Linux, and we'll do some coding examples. Let's give some credit where it's due. If you really want to understand assembly language programming, I would suggest to read these two books. These two books are written by the same author, Jonathan Bartlett. The only distinction between these two books is the one at the top covers 32-bit and the one at the bottom covers a 64-bit operating system. These two are excellent books to learn assembly language programming. Alright, let's look at an overview of CPU architecture. If you look at any modern computer, you'll see these three main components. You have central processing unit, in short CPU. Then you have the main memory, also called the physical memory, also called the random access memory, in short RAM. And then you have input and output devices. These are your keyboard, mouse, monitor, external devices like hard drives, etc. The CPU is also called the brain of your computer. And let's see what is inside the CPU. The CPU has multiple components. It has something called an arithmetic and logic unit, in short ALU. This unit is responsible to perform all the arithmetic and logic operations. For example, if you want to add two numbers, divide two numbers, compare two numbers, those kind of operations are performed by the ALU. Then you have registers. Registers are memory locations. These are available inside the CPU. These are extremely fast both for storage as well as retrieval by the CPU. These are some of the common registers. PC stands for program counter. This register is responsible to store the memory address of the next instruction that the CPU is going to execute. Instruction register, also they call the IR register, is the register that holds the current instruction CPU is executing. E-flags register is the one that stores information about the previously executed instruction. So for example, if the result of an addition becomes 0, or the result of an addition involved a carryover or an overflow, that information is stored in the e-flags register. And then you have more general purpose registers we will see as we go through the sessions. We also have another unit called the control unit, which is kind of an orchestrator or a manager, so to speak. This generates signals so that ALU registers and memory, these units can work in tandem. Now let's look at how CPU executes instructions. CPU goes through a cycle called a fetch, decode, and execute cycle to execute any instruction. And let's see what that is. Let's assume the program that you want to execute is already loaded in memory. So the one that you see on the right side is your program that you want to execute, and the numbers that you see on the left side are the memory addresses. Don't worry about this. We will look at what memory is and how it is organized shortly. All you have to understand right now is the program is loaded in memory and each location in memory has an address. So the first phase that the CPU goes through before it executes an instruction is called the fetch phase. So before CPU can fetch anything from memory, it has to know from where it has to fetch. And that's where the program counter comes into the play. Program counter stores the memory address or the memory location from where the CPU will have to fetch the next instruction. So now that we have 102, as part of the fetch phase, it goes to address 102 and fetches this instruction. Once the instruction is fetched, it goes to the next phase, which is the decode phase, where the CPU tries to decode what this instruction is all about. For example, this is an add instruction, which says add the number 5 to whatever is available in this register and store the result into this register itself. So that's what this instruction says. So at the end of the decode phase, the CPU understands what to do with this instruction. The next phase after the decode phase is the execute phase. So let's assume that our AX register currently has number 10. So as the CPU moves from decode to execute phase, the CPU instructs the ALU, which is the arithmetic and logic unit, to perform this addition operation. And as we just saw, this operation does add 5 to whatever is available in this RAX register and stores the results in the RAX register itself. So it picks up the value of 10 from RAX, adds 5 to it, and then you have 15 as the result of the execution. The next phase is the store phase, where it takes the result and stores it back into the RAX register. And that's one fetch, decode, execute, store cycle. After this is done, as we just saw on the previous slide, if this operation resulted in a carryover or overflow bit or resulted in a 0, then the E flags register gets updated appropriately. Now the CPU is going to execute instructions after instructions until we tell the CPU to stop. So having executed instruction at 102, it'll start moving on to the next location. So the program counter gets updated to 103 and then goes on to the next fetch, decode, execute cycle. That's how CPU works. Let's look at memory and registers. So memory is nothing but storage locations. Anything that you can store and retrieve is what this memory is all about. So if you look at these individual boxes that you see 8 boxes. These individual boxes are nothing but storage locations. And what you can store in these individual boxes are either 0 or 1. You cannot store anything other than a 0 or a 1 in each of these individual boxes. Each individual box is called a bit. It's called a binary digit. In short, it's called a bit. Binary meaning it can only store either a 0 or a 1. And that's why it's called a binary. And since these are digits, it's called a binary digit. In short, it's called a bit. So each individual box is called a bit, and a collection of 8 bits is called a byte. And each byte has an address, which is nothing but the memory address. So in short, memory is nothing but storage locations where you can store and retrieve information. A single storage location is called a bit. 8 bits is collectively called a byte, and each byte in your computer has an address which is called the memory address, or nothing but the memory address. So if you look at your computer, you'll have a large collection of storage locations. These are 8 bits wide, or in short, a byte wide, and you'll see a large collection of memory locations or storage locations in your computer. Each of these memory locations have an address. These are byte addressable, as we saw in the previous slide. Each individual byte has an address which is nothing but memory address. And one thing that you have to keep in mind is the CPU will never access one single box at any given time. It will never access one single box at any given time. It always accesses a byte or more than a byte or multiples of bytes. So this is how memory is organized. You have large collections of storage locations. Each byte is addressable by a memory address. And what you can store in these locations are only zeros and ones. And what the information that gets stored in these boxes can be either instructions or it can be data. The CPU will never distinguish whether what is stored in these locations are instructions or data, because at the end of the day, these are zeros and ones. It doesn't distinguish and doesn't matter from a CPU standpoint. There are other techniques used to understand if given a combination of zeros and ones are instructions or data. So how do you access information from memory? Let's say you want to access one single byte. To access data from memory, all you need to know is you need to know the memory address or the memory location from where you want to read, or whether you want to the memory location that you want to write, and then how many bytes you want to read or write. Let's say you want to read 1 byte from memory location 1005. You go to the address 1005 and then retrieve 8 bits or retrieve 1 byte from that location. If you want to access 2 bytes, you go to the location 1005 and then access 2 bytes. If you want to read, let's say, 4 bytes, you go to the location that you want to read from and then you read 4 bytes from that location. That's how memory is organized, and that's how you access these memory locations. Registers in x86. RAX register, A stands for accumulator. This is the register which is commonly used in arithmetic and logical operations. This is one of the most popular registers. It's also used in storing the system calls when we invoke system calls. It also stores the return values from functions. We'll look at these registers in detail when we do the programming, when we do the coding exercises. This is just a quick summary on what registers are available and what they are. RBX is also called the base register. It's commonly used to hold data or addresses. RCX is called the counter register. It's often used in loops and string operations. RDX is a data register, typically used to hold the remainder in division operations. For example, if you want to divide 11 by 2, the remainder 1 is stored in the RDX. RSI and RDI, these are the source index and destination index registers. These are typically used in string operations. RBP is called the base pointer. It's used to access function parameters and local variables on the stack. RSP is a stack pointer which points to the current position in the stack. We'll look at RBP and RSP at greater detail when we talk about functions and stack, etc. And then you have a set of 8 registers, R8 to R15. These are additional general purpose registers available for assembly programming. Now let's look at addressing modes. What is an addressing mode? Let's explain this with an example. So move is an instruction. It says move whatever contents are available in the RAX register to RBX register. So in the assembly language parlance, we say move is an opcode, and the data it operates on are called operands. So addressing mode, in short, provides information to the instruction about two things. Number one, it provides where is the data available, meaning is it available in registers or memory, or is it available as part of the instruction itself, in which case we say it's an immediate mode. So it provides information about where these operands are available. Again, whether it's available as part of a register or a memory or immediately available. And second thing is, it provides information on how to access that information. So even though the data is available in the register, is it directly available or indirectly available? So don't worry about that. We'll look into that with very specific examples in the next couple of slides. But the key takeaway here is addressing mode basically provides clues about two things. Where are the operands available, whether it's available in registers or memory, or is it immediately available as part of the instruction itself, and how to access those operands, whether it is directly available or indirectly available. Let's look into some of the common addressing modes available in x86. So this is an immediate addressing mode. So in the immediate addressing mode, let's see how the operands are available for the instruction. So let's assume these are the contents of the registers. So we have R, AX, B, C, X, and DX. And these registers are 8 bytes wide. We are talking about 64-bit operating system. So each register is 8 bytes wide. Let's assume RBX has the value 2. So in the immediate addressing mode, this is an example. So move $1. Dollar basically you can think of it as a constant. So move $1 to RAX. This indicates move the number 1 to the RAX register. So the reason why this is called an immediate addressing mode is because the data or one of the operand has data which is available as part of the instruction itself. So the CPU doesn't have to go to a register or a memory or any other place to access this source data. The number 1 is available as part of the instruction itself. Since it's immediately available as part of the instruction, it's called an immediate addressing mode. So what happens when move $1, RAX is executed? The value number 1 is moved to the RAX register. Let's look at another example. So here's an add instruction. It says add number 5 to whatever is available in the RBX register. So when this instruction gets executed, no surprise, the number 2 which was already available in RBX gets added with number 5 and the result is stored in the RBX register. So that is the immediate addressing mode. The key takeaway here is the data is available as part of the instruction itself. So it's immediately available for consumption. That's why it's called an immediate addressing mode. Let's look at another addressing mode. It's called a direct addressing mode. And again, these are the contents of the register. Right? Currently, we have these 4 registers, no data inside the registers yet. And let's assume this is the contents of the memory. So we have memory location 1001, 1009, 17, and 24. Again, keep in mind the addresses are 1001, and then the next address location is 1009. The difference is 8 bytes because each of this memory location is 8 bytes. Let's assume the contents in the location 1001 is number 10. In the direct addressing mode, one of the operands basically provides the memory address from where the CPU will have to take the data from. So here, move 0x stands for hexadecimal. So basically, it says the 1001, the number 1001 is not a decimal but a hexadecimal number or hexadecimal value. So it says move the data available in this address to whatever is available in the RX register. So basically it says move the data available in this address to the RAX register. So when this instruction gets executed, CPU goes to this address 1001, picks up whatever data is available in this memory location and moves the data to the RAX register. So this is what happens. At the end of this move instruction, the CPU goes to the address 1001 and picks up the value 10 and pushes it back to the RAX register. So in the direct addressing mode, the memory address is available as part of the instruction, and CPU will simply go to that memory location, read the contents, and does the operation that's requested as part of the instruction. Let's look at another example. Now here, this is a move instruction. It says move whatever is available in the RCX register to this memory location. Again, this is a direct addressing mode, and that's why you see the address directly available as part of the instruction. So the key thing is the memory address can be part of the source, or it can be part of the destination, or it can be part of the target. So the previous example, we saw the memory address was part of the source operand, and in this instruction we see that the memory address is part of the target operand. So when we execute this instruction, CPU goes and basically CPU instructs to pick whatever information, whatever data is available in the RCX register, then go to this memory address and store the value. So RCX already has value 5. Once we execute this instruction, value or the number 5 should be stored in this memory location 1017. And that's what happens when this instruction executes. So the takeaway for the direct addressing mode is the memory address is available as part of the instruction. One of the operands could be the memory address, and it is available as part of the instruction itself. And the memory address is directly accessible, meaning the value or the data is stored directly in that address, or the data is read directly from that address. Let's look at indirect addressing mode. These are the contents in the register, and these are the contents in memory. So keep in mind the memory is 1 byte wide here. So the memory address is starting from 1001, it increments by 1 and goes up to 1012. So let's look at the indirect addressing mode with an example. So here's an instruction. It's a move instruction which says move. There's an RAX register within the parenthesis, and then there's an RCX register. So the difference between the direct addressing mode that you saw in the previous slide and the indirect addressing mode that you're seeing here is the open and closing parenthesis. So the indirect addressing mode will have the open and closing parenthesis. So in the indirect addressing mode, what this says is go to the RAX register, see what is stored in the RAX register, which is 1001, and don't move the data, don't move the contents of RAX directly, but go to the actual, consider that as a memory address, go to that location, and then access the contents stored in that location. By the way, how much data you want to access, and that's what is indicated by this Q. Q stands for quad word. Word is 2 bytes and quad is 4, so it is 8 bytes. So what this instruction says is go to RAX, find out what the value is stored in RAX, consider that as a memory address, go to that memory address, and then read quad word, which is 8 bytes. So if I run this instruction, what will happen is the CPU goes to RAX, follows RAX, which is 1001, and then reads 8 bytes, whatever is highlighted here, and then moves the number 8 to RCX. That's the indirect addressing mode. I want to highlight a couple of things. So we are talking about 64-bit operating systems, and we're looking into the registers and the assembly from that angle. So in 64-bit, the registers are 8 bytes wide, which is, you can see these boxes, individual boxes are single byte. So each of these registers are 8 bytes wide. Now you can access these individual boxes. The lowest two boxes that you see here are DL and DH. L stands for low and H stands for high. You can actually access those individual boxes as DL and DH individually. Or if you want to access them as 2 bytes, which is 16 bits, you can refer to them as DX. So if I move something to DX, then that value gets moved into these two boxes, the lower two boxes. Likewise, if I refer to the, if an instruction refers to EDX, then it refers to the 4 bytes, the bottom 4 bytes of a register. In this case, EDX refers to the bottom 4 bytes of the RDX register. And likewise, if it's RDX, which is what we have been using in this lectures, RDX refers to 8 bytes. That being said, let's look at this instruction. It's move B. B stands for byte. There are different variations of move instructions. So there's a move B, which is a single byte. There's also move W, which is meaning move a word. A word is normally 16 bits. And then you have move L, which is move long, which is going to move 4 bytes. And then we saw move Q. Q stands for quad word, which is 8 bytes. So move Q is going to move 8 bytes. So in this case, we are moving a byte. Move B, RBX inside the parenthesis to DL. So what this instruction does is, go to RBX. RBX stores 1001. Consider RBX as a memory address and go peek into that memory address. So that'll be like, we'll go to 1011 and we'll peek into it. It has number 5. And then move that to DL. DL is the lowest bit in the RDX register. So if we run this, that's what's going to happen. We went to RBX, followed through the memory address, peeked into the location of 1011 and moved that into DL. That's how indirect addressing mode works. Alright, let's move on to the next one. This is called an indexed addressing mode. Indexed addressing mode is typically used to access an array of information. You know, if you have programmed in high-level languages like C or C++ or Java, whatever it is, you might have heard about this term called arrays. Arrays are a collection of similar data, let's say a collection of numbers, a collection of strings, a collection of characters, basically, which is called a string. So we have a collection of data, like-minded data, that are available one after the other. So if you have an array, a collection of data, then you can access them one after the other using this indexed addressing mode. So to see how this indexed addressing mode works, let's look into the assumptions that we have. So here are the registers that we'll be operating on. So we have RAX, BC, DX. RCX currently holds 0. Array start, this is a variable. You can define variables in assembly as well. So ARR underscore start is a variable, and this variable currently holds 1000 as the data. And here's a memory, and let's look into the contents of the memory. And each box here is 8 bytes wide. So the memory starts from 1000 and goes up to 1008, etc., to 1088. And these are the numbers stored in these locations. Array start variable stores number or the memory address 1000, and that's where the array starts. So you have an array in memory. You have a bunch of numbers. How do we access these data one by one? That's where the indexed addressing mode comes into the play. So this is how you access it. So here's a move instruction. What's more important is this piece. So array start is actually a memory address, right? This array start. So you start from the memory address, open parenthesis, close parenthesis, comma. We'll talk about this later on. At the parenthesis, there are 3 pieces of information. The second piece here, what you see is RCX, that has to be registered. So we are using RCX register here. RCX holds some number, which is nothing but the index. So this is the index to this array. So array start actually stores 0, so it's 1000. This is where the array is starting. And then RCX basically keeps track of the index. If it's 0, then this is the 0th index of the array. If it's 4, for example, 0, 1, 2, 3, 4, then it refers to this index. So RCX basically keeps track of the index. The third parameter that you see inside the parenthesis specifies the width of the data or the length of the data. So here we're talking about we're operating 8 bytes wide. So that's why you see the number 8. So what this basically means is go to this array start location. So go to this location, which is 1000. And then what you see inside the parenthesis, the RCX holds or keeps track of the index. Index times, this is called scale. Scale is how wide your data is. Index times scale. And whatever that value is, that's the resultant address that you have to move the data from. So RCX holds 0. So RCX is 0 times 8. This turns out, this whole expression turns out to be 0. And array start is basically 1000. So if you add this, it comes down to 1000. So to access the 0th index for this array, go to this location 1000 and read the value and move to RAX register. So if we execute this instruction, 20 gets moved to RAX. That's for the index 0. Let's say we want to access the index 1. Again, we go to the start of the array, which is 1000, plus this is the equation. This is how this whole operation, or this is how this whole expression is evaluated. So the array address comes in, plus whatever this parenthesis evaluates to gets added to get to the target address. So it goes to the array start, which is 1000. RCX tracks the index, so which is number 1. Scale, or the scaling factor here is 8 because we're operating under 8 bytes. 1 times 8 is 8. So 1000 plus 8 is 1008. That's the address to access the first index in the array. And as you can see, that's where it is. So when you execute this one, CPU basically provides instructions to go to location 1008, access 8 bytes, and then move to RAX. And that's what will happen. Likewise, if you want to access second index, same thing, go to the location of the array, plus RCX is 2 times 8 is 16. Then you move the data from 16 to 44. And that's how you access it. Let's see one more example, number 3, and let's see one more example for 7. So let's say you want to access the 7th index. Remember, arrays start with 0. We don't start with 1. So when we're talking about 7th index, we're talking about 0. 1000 is the 0th index. 0, 1, 2, 3, 4, 5, 6, and 7. So to access the 7th index, this expression should turn out to 1056. And let's see. So it goes to 1000. Array start is 1000 plus RCX is 7 times 8 is 56. 8 is the width of the data. This is 56. So 1000 plus 56 is 1056. And that's how the 7th index, 1056, gets moved to RAX register. That's indexed addressing mode. It is used to access collections of data, typically arrays or strings, and move through one after the other and start operating on that data. Let's look at another addressing mode called base pointer addressing mode. And here are the prerequisites. Let's assume registers. These are the contents of the registers, and this is the contents of the memory. Again, here memory starts with this is byte wide. This is only 1 byte, and so from 1001 to 1008, and then you have different numbers here in memory. So before we look at the base pointer addressing mode, let's refresh our indirect addressing mode because it has more similarity with the indirect addressing mode. In the indirect addressing mode, we saw this is an example for indirect addressing mode. So here's a move instruction. It says move open parenthesis RAX register close parenthesis and then to RCX. So what this instruction says is go to whatever is pointed by the RAX register, which is 1001, peek into this location, and then move quad, which is move 8 bytes to RCX register. That's what the indirect addressing mode says. So if I say this, if I execute this instruction, now CPU will go look into the RX register, which is 1001. Since it's an indirect addressing mode, I'll have to go to 1001, look inside the contents, which is number 8, because I'm accessing 8 bytes, and then move this 8 to RCX. That is indirect addressing mode. The base pointer addressing mode has a slight addition to it. So here's an example. Instead of, so whatever you did in the indirect addressing mode, you do exactly the same. The only thing is you see a number in front of the parenthesis. So what this says is, this is an offset. So go to RAX, right? Go to RAX register. Since there's a parenthesis, you'll have to peek inside the contents or contents of 1001. But before you do that, you add number 10. Basically, you offset this address to number 10. So basically what this is, 1001, RX has 1001 plus 10, which is 1011, and that's the resultant address. Then go to that address, peek inside the location, and then move one single, because we're saying move B, meaning move a byte, and then move that byte to the lower part of RDX register, because we're saying %DL. So when we execute this one, what happens is RAX register has 1001 plus 10, which is 1011. So we go to 1011, look into this contents, basically it's number 5. We are moving a byte to location DL. So DL will be something like here. That's what will happen. So that's the base pointer addressing mode. It's kind of an indirect addressing mode with an offset. You can think of it that way. It's heavily used in accessing your, when you talk about functions and stack, it's heavily used in accessing function parameters and local variables, etc. So it's a very powerful technique that we'll be using in functions. So that's it. So there are other addressing modes as well, but these are the popular addressing modes and more frequently used addressing modes. If you know these addressing modes, you can pretty much do anything in assembly. Let's just recap what is an addressing mode then. So addressing mode, as we saw with this example, move is an opcode and RX and RBX are operands. And addressing mode specifically provides two things. It says where the data is available, whether it's available in the register or memory or immediately available as part of the instruction. And second thing it provides information is about how to access the data. Is it accessible directly or is it indirectly accessible? That's what is all about addressing modes.